Now, welcome to this third part of our number systems tutorial, and in this series we're going to be looking at the conversion of numbers. Now, we're going to make the videos, the tutorials from now on, and then the other ones that follow a bit shorter, so that we can easily understand. We don't want to make them very long, so we're going to be taking them into parts. So, but all in all, at the end of this tutorial, we should be able to convert binary numbers to octal, binary and octal number system to decimal. Then also we should be able to convert decimals number system to binary number systems and octal number systems, and then interconvert the hexadecimal and the decimal number systems, and then also interconvert the decimal, hexadecimal number systems and the binary number systems. So we're going to start with converting a decimal to a decimal. But before we go further, we want to look at the possibilities that exist under the conversions of number systems. So I've got a whole lot of possibilities, which means we're able to convert from this number system to a vice versa, or from decimal to octal and vice versa, from octal to hexadecimal and vice versa, from octal to binary and vice versa, from decimal to hexadecimal and vice versa. These are the possibilities that lie. So we will try to find time and explore each of these possibilities. Now, a quick example that we can give is converting, we've got 25 there in decimal. We're saying that this one is equivalent to this in binary, and is equivalent to 3.1 in octal, and is equivalent to 1.9 in hexadecimal. So the 10 there is our base, and then the 2 here is our base, the 8 here is our base, and the 6 there is our base. Now, converting from decimal to decimal, as we have seen here, we're going to use this example. This is just for fun. We're going to have a number here, 125 in base 10, and if we want to convert it to decimal, we're simply going to be multiplying it by the base. Now, the base will have its power according to the position of that figure in the number. So, for example, 5 is the first position, it's the rightmost, while 1 is the leftmost. So the rightmost will be raised to the power of 0, so it will be 10 to the power 0 multiplied by 5. And then the next one will be 2 times 10 raised to the power 1. And then the next one will be 1 times 10 raised to the power 2. Now, after we have gotten our answers here, we simply add the results there, which will give us 125. So we have proved that 125 in base 10 is actually 125 in base 10. Now, the weight and the base is illustrated with our pictures there. Now, the next step that we look at is to convert from binary to decimal. So from binary here, going up there to decimal. Now, the steps to do that is you're going to multiply each bit by 2 raised to the power n, where n is the weight of the bit. Then weight is the position of the bit starting from 0 on your right. Then after we do all this, we're going to simply add the results. Or we can simply say any binary number can be written in expanded notation as the sum of each digit times the digit's place value. Now we have an example there. Our example is to convert from binary to decimal. So I've got this number here, which is in binary form. You can see that from the number we've got a base 2 there, and I've got 10 there, which is in base 10. We're going to get to this later on. Let's look at how we got to this number here. So I've got 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1. Now, we're going to be multiplying each of these figures here by 2 raised to the power of its weight. So the first one here will be multiplied by 2 raised to the power 0, which is this one here. The second one times 2 raised to the power 1, and so on and so forth. Now, after we've done all this, we're going to add the results. And the results will give us 43 in base 10. So that's our weight there, and we have a bit 0 there. The second example that we have is we can still do the same thing, but in this time we have just put it as straight in a straight line. But it's basically the same thing that we have here. So we have got 101011. We're saying that the first one here is the leftmost, which is this part. We multiply it by 2 raised to the power 5. While the first one here is the rightmost, which is this one here. You multiply it by 2 raised to the power 0. Okay, and then after the multiplication you simply add the results. Now, since each power of 2 is weighted by either a 0 or a 1, the binary number is simply the sum of those place values in which the bit 1 appears. The sum at once gives us the decimal equivalent of that binary number. Now, the next one that we look at is converting from octal to decimal. So for this one, it's basically the same way like we did in the binary form, just that now we'll be multiplying each bit by 8 raised to the power n, and n being the weight of the bit. Then after we do that, we're going to add the results. So we have an example here about 724. We're saying that the place value for 8 is 044. Then the next one will be 8 to the power 1. The next one will be 8 to the power 2. After we've multiplied this part, we get these answers here, and then we simply add them. Then we get our answer as 468 in base 10, as the equivalence of 724 in base 8. Now, converting to hexadecimal also is the same as we did with the other number systems, but this time we are dealing with 16 raised to the power n, where n is the weight. Now, we have to also explain that under the hexadecimal number system, we have numbers that move from 0 to 9, and from 9, after the next number that we get is a letter. In this case, it becomes A up to F. Now, the A up to F are 6 digits, and these digits are also given their equivalence decimal number, so which means the A is equal to 10, the B is equal to 11, the C is equal to 12, the D is equal to 13, and then the E is equal to the E is equal to 14, and then the F is equal to 15. So let's take, for example, we have an example where we have to convert ABC in base 16 to base 10. So our C is equivalent to 12, our B is equivalent to 11, our A is equivalent to 10. Now, we're going to multiply these equivalent numbers. We're going to multiply them to 16 to the power n, where the n will be the position of that number in the number that we are given. So, for example, our first number C is the rightmost, and it's in the first position, so it carries the power of 0. While A is the last one in this number, and it carries the power of 2. When we multiply these, we're going to now add the results, and which will give us 2748 in base 10, as the equivalent to A, B, C in base 16. Now, we're going to take a break, and then we're going to see each other in the next tutorial as we continue with the conversion. Thank you for watching.